Okay, I think maybe it's appropriate to move on to the field sampling methods, which is our next section. Better. Hey, hello everyone again. Talk. So the next section is talking about the pilot study. So it's field sampling altogether, but I'm focusing on the pilot study in this talk. And the overview of the talk, first I want to just review the objectives of doing a pilot study and just kind of put it into perspective. And then I want to define what I'm starting by calling an experimental unit. And it's a little bit important for the study, so I'm going to define it and talk about what I think that is at the pilot study, and then that'll expand to the field study eventually. We'll go on to talk about the field sampling package that we have, the sampling units, what's being measured and why. And then we've got some results from pilot field 1. We've completed one field. As you've seen, the meteorology has been a little bit hard to predict, and as Patty indicated, the expensive instruments don't like rain. And so if there's any indication of rain, we don't go out. We were able to sneak one field in, and that one's done. So I'll have some illustrative results to show it hasn't been fully interpreted yet, so it kind of leaves it up to us to still look at, and there needs to be more measurements, but at least it gives us a start to see what kind of things we'll be able to answer. And I'll finish up with lessons learned and some possibly additional tests and experiments to go on beyond the unit, experimental unit that we're going to talk about. So objectives of the phase 2 of this project. Now phase 1 was to go out and gather crumb rubber from the fields to send back to the lab to help us with method development, chemical identification, things like that. Phase 2 goes a little bit beyond that, and it's really meant to inform the development of the full phase 3 study. And so we want to collect measurements that are going to quantify, definitely try and help us quantify known pathways. Looking at the figure on the cartoon on there kind of illustrates the pathways. We want to collect measurements that can help us characterize some anticipated pathways. They may not be there, but we want to have measurements that can help us understand those. And then finally, if resources are available and an opportunity is available, we want to have measurements at least to help maybe discover unanticipated pathways. So it's really hard to measure what you don't know is out there, but if we have the tools to go out and look, we're going to try and include those in the pilot study. In another, I guess, sub-objective of phase 2 is just to get practice, the logistics part of it. And it's not always simple. Sometimes you don't even think of things, and just access to the fields, getting to the fields, understanding what's going to be there when we get there. Transport, setup, takedown, it's a lot of equipment to get out there. And so we want to be able to practice that operation and try and get as much of the variability that comes from us messing up out of the system before we head into the field and do the real study. And then handling all the data processing, how do we bring that in, package it up, interpret it, and send it back. And then always on these pilot studies is the opportunity to experience surprises. I mean, they're going to happen in field studies, and we just need to learn from them, adapt, and try and get as many of the surprises out of the way in the pilot study as we can before we move into the full study. Okay, so the experimental unit, this is kind of key for us because we can't measure everything, but at the same time, we want to have, when we go to a field, we want it to be fairly consistent because of the factors we're testing. We're testing climate, we're testing ozone, so we don't want to go to the field and have so much scatter and variability in how we conduct the experiment that we can't tease out the small changes that might be due to the environment or whatever. So we're suggesting that we kind of build on what I'm going to call an experimental unit. In statistics, the unit is that which receives the treatment. So essentially, the fish aquarium would be the unit, for example. In practice, for us, we're defining the unit as a location on the field and of a specific size and orientation to the dominant wind and things like that. And I'll show you an illustration in a moment, but the idea is the experimental unit is going to provide us with some consistency, like I said, across fields, so we can compare other things and not just our impact on the field. And it also provides us, the intent is to provide us something to build on when we bring humans into the picture, because eventually the human subjects are going to be a part of this study, even if they're just putting energy into the field and agitating the field. They're actually going to be real people, and we want to have some way to contain that activity so we're not sort of herding cats around. We want to have some sort of framework for them to work within when we go to these fields. So what we're proposing, or what we've started doing, at least in the phase 2 study, is essentially an area, for example, on a soccer field about the width of a regulation net and the depth of about a penalty box. And the reason for that is we want to add energy to the field because of the conversations we've had about particles. But we also want to have that in a way that we're not chasing balls all over the field. So that put a net behind it. And obviously, if you have a soccer field, the best place to get a net is the goalie box. So that's where we sort of built, it's kind of just a logical building up of a system that we can repeat from field to field. Part of this experimental unit is this soccer ball kicking machine, which is just a monstrous pitching machine, if you've seen in baseball. And they work similarly to what you see in baseball. They just launch the ball and at very fast rates. I mean, they're launching them out there pretty good. So you set it up to where it actually impacts in a particular zone, and then we set the samplers around that zone to presumably capture anything that's resuspended or stirred up by the activity. And it turns out, although we're not supposed to use human subjects, when we didn't use human subjects, but somebody has to kick the ball back. So we had a few people hanging around in front of the samplers tossing the ball back, and that kind of gives it some structure. A surprise to me, it turns out not all fields are soccer fields. I didn't even think this through. I don't know why, but I was thinking soccer all along. So we actually have an alternative unit, experimental unit, that's defined here in the last bullet, but it essentially does the same thing. It just turns so the dominant wind blows towards the samplers, and it runs a ball down, just received by somebody downfield and returned. So another nice thing about having this kicking machine as part of our system is it kind of controls the rate of action on the field. So you can turn it up or down, and then if you get the humans involved, they respond to the machine instead of just scattering. So it gives us a little consistency. So what are we measuring? Again, we want to measure, at least for the pilot study, as much as we can to try and capture known things. We want to know as much as we can about particles, for example, gas-phase chemicals. So we're putting instruments on board to try and capture that information. And then, we have other instruments available, so we sort of rolled out some redundancy to try and make sure we capture everything we think we want to. So I'll just go down through the list here. There's 2 slides of these to start with. Every sample location, which to start with, we have 3. We're going to have a sample location on each side of the activity and one behind, and then depending on how the field's laid out, there'll be 3 distributed, at least for the start. If we don't see a lot of variability, we can collapse that or expand that. But every place we do a sample, we've got a 3D anemometer that gives us continuous wind speed and direction. We thought that might be important. Ambient temperature and humidity, these are just standard parameters that if you think about what you're going to put into a model or some interpretation. We actually put some probes in and looking at field temperature at depth. So we've got surface temperature with an IR measurement and then probes going down into the surface to try and look at the gradient of temperature. Not real informative in the winter, but it might be useful in the summer. We've got an ultrafine particle counter that counts basically all particles from super small, 7 nanometers, up to a 2.5 cyclone cut. So it gives you a particle count in the ultrafine all the way up to 2.5. We rolled out an aerodynamic particle sizer because we as you have same questions. What particles are going to be of interest here? What's changing? And so that instrument should give us from 0.3 microns up to 20, up to big pieces, a good sense of what's being resuspended. And then we've got the PM 2.5, PM10 numbers, which are continuous. In this case, we can also roll out filters in the future. We're using dust tracks that give you 2-minute average concentrations. So in addition, on the other carts, we've got an instrument that gives us size resolved particle number concentrations in bins, 5 size bins, similar to the one that counts all particles, but this one's breaking them into size bins. Total particle mass on a filter, and this is a medium to high vol filter that we're using for the SVOC samples. You can see it on the picture I'll slide the mouse over. This little sample train right here with the foil wrapped around it is a sorbent train with a polyurethane foam in the front and XAD, which is another sorbent that's stronger in the back and the outlet side. And on the very front end of this is an open face total suspended particle filter. So you're getting total suspended particles on the front end of that while you're collecting semi-volatile particles over a 3-hour period. So that's a good size particle sample for the semi-volatiles, and we have that at 3 different locations. Volatile organic chemicals, these are 1-hour integrated samples, so you're going to get several of these over the course of the period. A little bit smaller samples, but you get a lot of them. Volatile aldehydes, particularly formaldehyde and acetaldehyde, and I already mentioned the surface temperature. So that's what we rolled out for the phase 2 study. There's a lot of information to play with there. So now I'm going to just show some results, some information, not fully interpreted or fully vetted, but it'll give us something to kind of talk about and build on, hopefully. The first plot I'm showing is just environmental data. Actually, the first 2 plots are just environmental data. And it shows you, obviously that it was fairly cool out. This is wintertime, so it's not our ideal temperatures, at least what we expect from the modeling and the thinking that we put into this. It's fairly cool in the 20 degree Celsius range. I should get a chart with Fahrenheit as well to present, but that didn't roll out. Humidity's fairly constant across the day, and the surface temperature, that's measured by an IR kind of a camera almost, where you set that up on the cart and point it in the surface. And you can see here there's some there's some fairly similar lines all the way across it, but there's one place where this diverges, and the surprises thing, we should think about where shade is. And so the instrument that we put up actually created shade as it moved across. And so there's some adjustments there on the method to make sure we don't check the temperature in the shade. So those are just an example of lessons learned. The wind throughout the day, I've got this broken into 1-hour sections because that's the smallest section for VOC samples. We also combine it, the whole thing for the SVOC sample, for example. And it shows you in the morning, basically, that it's, again, we did our homework before we went to this field, and clearly the wind always comes out of the northeast, always. And then leading up to that, the week before that, we checked every day. And we got there and it completely came from the opposite direction after we set up. So, stuff happens in the real field, and clearly I think as the year goes on and we get into summer, the meteorology will be a little more stable and we'll be able to predict this better. But the intent was to orient the net or the kicking area where the material that's resuspended would come into your sample. And in our case, it tended not to, at least not the whole day. As the day went on, you got some more variability as you look down lower, especially the last hour of sampling. You tend to get a lot more variability, some wind coming from the west, which none of the records show it should come from the west or to the west from the east, but it did. So these are samples of particles, and on top is the total particle count, so total particle number concentration, the top red line. And here I've got on the chart, it shows where we actually had the kicking activity, the ball being launched into the net and sort of bounced in front of the net. And it shows this first large hump, again, this is not carefully vetted data yet. That first large hump is almost certainly the instrument warming up before it gets stabilized, and so there's some efforts we need to do to get things settled before we get going. But the rest of the period, you see fairly constant number concentrations on this field at this one measurement. The particle mass from the dust tracks, these are PM2.5 and the PM10, these lower figures, again show fairly constant concentrations and not a lot of change due to, at least visually, due to kicking. I'm not going to interpret this too much, but when the kicking stopped at this point here, there is apparently a change in particle mass concentrations. Again, not going to go into too much depth with this one instrument because we have to get some redundancy and learn some lessons, but it does start to show us a few things. This chart gives you information more on the size fractions, the major size fractions. And we had one instrument of the three that actually survived the morning. The duplicate MET1 we have stopped working because of a GFI problem on one of the cords. We reset the GFI immediately, but didn't start logging again on that particular device, so didn't get information. We got one information from one MET1, and that's what's shown here. It's a little bit more intriguing, I suppose, because you see when the kicking starts, you see a clear increase in, this is estimated mass from just the total particles, and similarly when the kicking stopped, you see a clear drop. Not huge numbers, not changes, huge changes, but another thing to notice is the size fraction composition seems to change a little bit when the kicking begins, and you seem to get a little bit more of the 2 to 3 micron range in the system, and that again sort of shifts, and these are small shifts, and so we want some redundancy. The other instrument I had for redundancy was that aerodynamic particle sizer, and unfortunately the team was getting used to the kicking machine and launched one over the net and just whacked it. And so it didn't play the rest of the day with us very well. And it pulled a communication cable out and nobody noticed that. It was still working, but so we didn't get the redundancy we wanted, and we can't read too much into this single outcome, but it does give you a sense of the kind of information that we expect to get as we repeat this study over and over again. We haven't analyzed the chemicals yet, the VOCs, SVOCs, things like that. That's still in the lab to be done. We were putting together talks. So lessons learned. Like I already mentioned, not all fields are soccer fields, so we need to be prepared, but I'd like to build this study around what I'd call an experimental unit. So whatever field we go to, we do the same thing, and then let the field tell us what's going on after that. The next thing we learned is that actually not all fields, and I want to run this past, at least let the panel see this for your comment, not all fields have power, and I was surprised by that. There's not electricity at all fields, and so we had to deal with that, and what we did was we put together a 2.8 kilowatt gas-fired generator, and first thing I say is, well, shoot, now I'm putting emissions into the system. So we put the generator 100 feet away from our experimental unit, preferably downwind, although in this case you already saw what happened, but so 100 feet to the generator, and then over the generator we actually have a fume hood with 800 CFM of air that continues the exhaust on out another 100 feet. So the exhaust is diluted dramatically and then released 200 feet, presumably downwind or regardless. I mean, it's so diluted at that point, I think we're probably okay. So that's how we responded to that. A few other lessons learned. We initially got to the fields thinking they'd be empty. They're not always. There's people that will show up, and regardless what the facility guy says, people show up and play. So there's a need to try and deal with that with barricades and whatever. We've already talked about the wind. My approach is that to do, sort of do the best you can with your predictions and setup and then measure what you get. The other approach would be to just reorient things periodically, and that bothers me because I don't want to start stirring things up by the experiment. So generally we're going to do our planning in advance, set it up, and then do our best to get the wind direction right. And then obviously protect the equipment. We should do a little better job. Some additional measurements that we are considering, clearly for the next pilot and obviously for the field study, we're going to upgrade the high flow sampling head. It's a total suspended particle now, but we've got some 2.5 cyclones ordered that we'll put on that go at the 100 liters a minute flow rate. So those will be used to actually get a more relevant particle load on that filter. We still need to add a particle mass or PM sampler for the metals analysis, so that'll be on a cellulose filter, and again, it'll be a high flow filter. We'll try and collect mass. We have the opportunity to add smaller filters for particle mass. Again, it's only 2.5 and 10, but these are small, they're a couple inches across. They're fairly small filters with a lower flow, and you can distribute them more widely if we want to look at variability, spatial variability. And we have an opportunity, we can roll out ozone measurements too if we think that's important in some regions, we can do that. Additional experiments that we could do beyond just this unit, experimental unit that I've defined already. We could roll out at these different studies some VOC measurements that give us a sense of gradient by height away from the turf, so low, and then work your way up to breathing zone and maybe a little above that. We could spread out VOC measurements in transects and see what things look like across the field. Again, so these are just spatial variability measurements to help us understand how things differ. You know, if we measure something in point A, how does that relate to point B? I think the comment on returning to fields to get replicates, I think that's what I heard mentioned earlier, and that should be done. I think we don't have it in the experiment now, but we should return to fields and do the same thing and start getting a sense of what that number looks like. We've talked about actually putting replicates at fields if there happens to be a grass field nearby. Do just move the experimental unit so you have a comparison between on-field and off-field to start basically trying to tell a story. That's what we need to eventually do. There is a thought, and this is a little bit farther down the road. I don't know if this has been vetted at OEHHA or not, but we'd like to try and start working on the idea of some dermal exposure surrogates. And one might be, I know pesticide industry uses these cotton union suits a lot, but I don't think I'd go that direction because of the problem with heat, but maybe compression socks or compression sleeves, something along those lines that we could put on our human subjects, take off and run through the analysis and try and get a sense of what kind of things are sorbing to or sticking to the simulated skin. And then obviously we're going to bring human subjects into this, not as subjects per se, but they're going to work on the field and basically contribute to the activity and energy into the field. So that's kind of a fairly quick overview of first findings from pilot number one. We'll go out for another pilot study as soon as the weather clears, and then write this all up and decide on the final protocol for the field study.
Thank you, Dr. Medalena. So, general comments to start with. Ed.
So, several comments, some of which you may want to respond to, others just take under advisement. With regard to the fact that you found that there are fields that aren't just soccer fields, I think given the limitation to the number of fields that you can sample, you may think about just restricting it to soccer fields because you're not going to have enough information to differentiate between these different fields. It's just going to introduce noise into the whole equation. And if the focus is soccer field, just as the focus cannot be on track and all the other sports, I mean, there's just too many variables. So I think that would be maybe a key question that could easily be done.
Just before you go on, the time activity is just soccer, or were you going to go to other sports? Because, again, I think focusing on soccer, both for the exposure sampling
across
and
the study.
Yeah, across the study would be a good idea.
Secondly, it wasn't clear from what you did, but I assume, or maybe I would just suggest that wherever you do place your samplers, you use a GPS sampler to document where you are exactly with your sampling, just to be able to recreate. Thirdly, I wasn't quite sure what the total sampling duration, but it looked like maybe it was 3 hours integrated sampling at these locations. Do you do it at the same time of day? Are you purposely trying to look at variations across the day? Do you let it happen whenever it happens?
Yeah, it happens whenever it happens. Essentially, when we get access to the field is sort of the limitation. That's why we're trying to collect as many environmental factors as we can.
I mean, that's certainly the way soccer is played. They start from 8 in the morning, go to, whenever, especially if they have lights. But I don't know how you characterize that, but that's something. Next, in terms of warming up your particle instrumentation, you may want to put a zero filter, an absolute filter in the front of them, just to demonstrate that the instrument performance is consistently returning to baseline, and also then you don't have to worry about why you get these funny sort of blips, because it won't be there. And if they are, then you have an instrumental problem that you know is starting. And fifth, I would strongly encourage you to think about ozone sampling, because it was one of the criteria selections. There are a number of low-cost ozone sensors, and I think you ought to characterize what the concentrations are during the course of your exposures.
Thank you, Ed. Good comments. I'm sure that other panel members have comments about
I just thought also you might want to set up a video camera to sort of show what this ball bouncing looks like, because I think in terms of, the public understanding, they're going to want to see, like, okay, is it that image of the chrome rubber being stirred up or not? So it might be handy to have that. And then I wasn't clear, do you set up the soccer net, or was it the soccer nets, are you using the soccer nets that exist?
There's one on the field. Ideally, there's one on the field. I'd rather not bring our own equipment in, but it doesn't happen that way every time, apparently.
And then also, doesn't that restrict, then it only goes in two directions for the wind.
Well, the wind obviously is variable. I'm not sure I
Right,
understand
but
the question.
I'm just saying, like, if you predominantly have an east-west wind on the field, but the soccer nets are set up north-south.
Oh, they're easy to move with more than two, a couple of people.
Oh,
can
okay,
pick
so
them up
you're
and move
you're
them.
not leaving them where the soccer net would go. You're moving it to
I'm glad
somewhere
you
and
said
hoping
that.
it's there.
Correct. The
Okay.
idea is to orient it to where the net sees the most wind moving across the field. So in our case, I was expecting it to come north to south.
Right,
And I
okay,
just
and
left
then
it
you
where
just-
it was because it was already at the south end of the field. And so it was
Okay.
perfect in that sense. In this case, we had a baseball field behind us. So it was really almost in the middle of the turf area. But we were generating particles, in this case downwind, from the instruments most of the time.
And then I was just going to say, I actually, Ed had indicated it might be good to have a GPS to identify exactly where you were, but I was thinking that might be problematic because the fields might not want to be identified. So,
Just to clarify, for the purpose of the data, if you need to go back, you want to know where your samplers were, where you made your measurements.
I think that's a great idea. You can get fairly good precision with over-the-counter GPS, close enough, and it can be kept confidential. So it doesn't need to be shared with the data.
So the data you presented sort of brings up the issue, again, with the PM. There's a lot of collecting PM samples and measurement, and yet I'm not sure you can demonstrate that it's really from the crumb rubber. And so is there a way, will SEM on some of the samples help you to be able to distinguish what's crumb rubber and what isn't? We, years ago, down in Fresno, did, sort of the real-time particle monitoring from the ultrafines up. And all people had to do was walk in the house, and they'd just stir up all kinds of ultrafines and everything else. And there wasn't tire crumb there. It was just, stuff being stirred up. And I somehow think you need to sort of figure that out before you do a lot of the PM and attribute it to tire crumb. And I'm not sure how you do it, but I think that that's really important. The other thing is that, to spend all that time and effort collecting that many PM samples, if it's really not needed, I'm sure there are other places you can you can put those resources. The other thing, the dermal exposure, I know EPA is doing body wipes. I think they're doing right leg and left leg. When we were doing kids studies, we put little sort of cotton union suits on the kids. I think something that might be soccer socks might work well, but you've got to have the right material. There's a lot of stearic, there are a lot of fatty acids in that material, and you have to clean them up a lot, but there are people at EPA that know how to do that. They sort of provide you different things, but we found with the kids, the cotton suits actually collected enough material so that you could sort of see a lot.
Any comments to my left? Amy?
When you look at the outcome of this and these data, how are you thinking about what you're predicting? In other words, these are outcome variables, basically. And we have the climate variable, we have ozone, we have age. And those are the things that will be the predictor, things you're trying to predict from. Well, what else should we be predicting from? It seems missing here. In other words, is it something about the composition of the field? you know, do you understand what I'm saying? It's like we're saying, okay, we want to know whether there's ozone there, what the weather's like, and how old the field is. Is that it? Aren't there some other things that you would have learned in phase 1, or that you would look at from some additional sampling of actually the crumb that's in your experimental plot that would then inform what you get here? Or are we just assuming all fields are the same? See, it seems like there's a step missing here to me.
Yeah, I think you're probably, my focus has been on measuring exposure concentrations, right? And so the lab work is going to tell me what fraction of that exposure concentration is likely due to the crumb, because like benzothiazole is a rubber marker, okay? So if I see benzothiazole, you know, that's going to be most likely related to the crumb. But ultimately, we're measuring exposure concentrations over and on these fields of the chemicals that we've identified in
On the list.
identification process. Yeah.
And so wouldn't there,
Tease out whether those chemicals are strictly related to the field or from the field. For example, I mean, the particle measurements that we show almost are certainly just blowing across the field from, you know, the majority of them. At least early on and late, they may change compositions. The one instrument indicated there may be a change in size fraction, which would be, oh, okay, well, that's probably coming from what we're doing on the field. But
well, or would you expect to see a different mix at fields that had a different mix of chemicals? I don't see how you can see that in this design.
yeah, well, the samples we have of crumb are coming from every field as well. So phase 1 exercise, which is where you you actually collect crumb, that'll be done at every field as well.
And so you're going to include that in this design.
Yeah. I'm sorry. That was
It's not
phase
really-
1, and you're right. It's not real clear. I focused
It's not
on
clear
the
at
new.
all. And when you talked about it before, you talked about it as for methodological development and not as an input into the models that would
Oh, very
come out
good.
of the analysis of this data, and that's why I'm asking you.
Yeah, no, we're collecting crumb at each location as well, using the same method that was set up for the phase 1. And so we'll have a significant amount of crumb, and there needs to be a decision made at some point moving forward whether we could live with a composite sample of crumb from that field, or do we need all 10 samples? Because that's where the labor comes in.
And that is something that could be informed by your pilot, right? If you actually looked at what the variability is, that if it matters, that would be
Exactly.
something you could work out here.
And other agencies may be working on some of that as well to help get a sense of variability. So at a given field anyway, so that would help understand what's in the field itself and might inform us.
Well, if it doesn't, that would be informative too, wouldn't it?
Any other comments about field sampling?
So basically, the data from the pilot will help us gain information whether we should move on with a composite sampling or individual sample analysis. But we're collecting as individual because you can always composite later on. So we prepare for variability adjustment for the field that we sample now at this stage and make a data-driven decision further down. If we can do composite, maybe we can do more field. So we see more field across California when we have less intra-field variability. So it's going to be data-driven, we'll modify as it goes.
And also, in a way to address Amy's question, in phase 1, we did collect crumb rubber samples from both old and new fields. Try to get a little bit handle on the variability between how age would impact the field. But at the same time, we have to recognize, these crumb rubbers are highly variable and may come from different sources. But we did try to, look into that variable.
Yeah, and that's sort of the point. They're variable. So how is the variability in results just reflecting that variability, or what? I think it's going to be hard to interpret the exposure metrics if you don't have some understanding about how they relate to the source material.
Well, we're going to measure the variability, and I don't think we will have the resolution to understand, to be sure about the variability. On the other hand, kids play on the field. A lot of times they travel along California in the different field. So the idea is to look for the worst case scenario versus like an average exposure. If you go out for a game, for a tournament, for soccer parents, they have been telling us that they go all the way up to Reading and they go all the way down to LA. So we are not saying that you are only restricted to your homeland or home field. By having been able to cover California across, we get more idea about addressing the difference in chemical composition as well as chemical concentration in these fields that we can cover and try to build a worst case scenario from there. So that's the goal. Hopefully we will see one way or another the trend. We can help us modify the sample or redesign the sampling to be more address this issue.
Dr. Bennett?
On the field that you did do, how long had it been since it had rained?
Stopped raining the day before.
I'm just wondering if that's partly why you didn't see any PM, and I think,
The field was wet in the morning, and it was just gorgeous clean, and as it dried out, it even changed colors. So yeah, it was, but we needed to get out, and we needed to, the
Right,
first parts
right.
of that objective of just learn how to do the study. I mean, the data is extra. The pilot was to sort of learn these things, and
but it might be good for the second field to at least try and wait for it to be dry, but it might never dry.
Well, we hope that it will
Right.
dry.
Eventually it'll dry out, and remember, you used to have a big drought.
To address your concern, all our phase 1 field, we were so lucky. We collect all of them before this rain come. Not just this rain season. It was no rain within months before we actually sample. It was drought for years. And we collect them right before the rain come. And because the goal of phase 2 is more method, of course, it will be optimum not to have the rain. That's why we're moving the second part to Southern California. We're looking for areas that are drier and hotter and older to get a different spectrum that hopefully we'll see a different scenario here. Data.
Dr. Sheldon?
So maybe you've already said this and I missed it. But if you are collecting the crumb rubber at every field and you're collecting all of these samples and you're doing the modeling, you should be able to relate for each field what is in the crumb rubber to what you are finding in the exposure samples, which will allow you to hopefully tease out what are the exposures due to the crumb rubber. That's the whole idea, right? And so that should help some of the issue that you were bringing up. But so
She was bringing up the issue because it wasn't clear, and now it's clear.
okay. Thank you.
One other specific question that staff asked me to have you consider is, do we have any suggestions about ways to collect SVOCs adhered on PM 2.5 particles? I'm just reading my question here.
that actually, it was an interpretation of
Okay,
the question was more whether we should concern ourselves with
With
the
SV.
known artifact of blow-off of particles, or can we assume that the material, the chemical that blows off the particle, it might be in the particle when it's in the atmosphere, but it may end up in my sample and look like gas phase. Can we assume that's 100% bioaccessible and just move on and not worry about it? That piece came off easy enough that it contributes to inhalation.
yeah, thanks for that clarification.
Also, that's the way that reading EPA's study plan that they are doing it. They're combining both the particle and the vapor phase together. So again, with this consistency thing, and you can model it, right?
Good, so I think we're finished with this section.